Okay, we're now in section 18.2, resistors in series. There's our PowerPoint. All right. Make sure. That's the right spot. Okay, when two or more resistors are connected end to end, as in the figure on the left, we say they are in series. You've already seen capacitors in series and capacitors in parallel. Now we're going to be discussing resistors in series. The resistors could be simple devices, for example, light bulbs or heating elements, or the little resistors that you use in the lab. When two resistors R1 and R2 are connected to a battery, the current is the same in the two resistors because any charge that flows through R1 must also flow through R2. This is analogous to water flowing through a pipe with two constrictions corresponding to R1 and R2. Whatever volume of water flows in one end in a given time interval must exit the opposite end. Because the potential difference between A and B in the middle figure equals IR1, and the potential difference between B and C equals IR2, the potential difference between A and C is given by this equation. Oops. There we go. Delta V equals IR1 plus IR2 equals I times the quantity R plus R2, R1 R plus R2. It doesn't matter how many resistors we have in series. The sum of the potential differences across the resistors is equal to the total potential difference across the combination. This result is a consequence of the conservation of energy. Okay. The circuit on the left can be drawn with an equivalent resistor, R equivalent, that can replace the two resistors of the original circuit, as shown on the right. The equivalent resistor has the same effect on the circuit because it results in the same current in the circuit as the two resistors. Let's apply Ohm's law to this equivalent resistor. Whoa. I just accidentally turned off my iPad. There it is. Let's apply Ohm's law to this equivalent resistor. We can extend our analysis for more resistors in series. Okay. So the delta V equals IR equivalent. IR equivalent equals I times R1 plus R2, or R equivalent equals R1 plus R2. Now, it doesn't matter how many resistors we have in series, the R equivalent is equal to R1 plus R2 plus R3 plus so on. In other words, it's just a simple sum of the resistors when they are in series. Okay. Note that the filament of one light bulb in our circuit represents the resistors here. Represented by resistors here were, if the filament of one light bulb in our circuit, represented by the resistors here, were to fail, the circuit would no longer be complete. An open circuit condition would exist, and the second bulb would also go out. This ends this section on resistors in series. The next one will be 18.3, section 18.3, resistors in parallel.